All right, so now we're going to take a part of a circle, semicircle if you will, where I want to find the electric field at what would be the center of the circle if you bothered to complete it. Okay, and I'm going to have an angle, which I'm going to describe as theta, and we're going to make it symmetric so I don't have to work nearly as hard doing all sorts of crazy math. All right, so this is going to have a total charge on it. If it has a total charge on it and it's evenly distributed, which is a requirement for this problem, I'm going to recognize that I'm going to have a charge per unit length. Okay, and that charge per unit length is going to be dependent on the length of the wire and the rest of the nonsense. And so, oops, I should write this as my charge per unit length. There's a couple different ways I could do this, but the bottom line is I need this lambda when I get done. So you'll figure out how to figure out what the charge per unit length is and call it a day there. Then I'm going to go ahead and do what we've been doing all along, which is kq over d squared is what the electric field caused by a single point particle somewhere sitting on this edge. Now what's interesting about this is there's going to be one, if there's one above, there's one below. So you have a cosine issue. The other thing that's interesting is this. Look what's not changing. The radius is not changing, right? So the radius is going to be a constant in this problem. So what's changing? The angle. Okay, so now I'm going to look at this and go, okay, well, I've got this is going to push down, this is going to push up. The up and down components are going to cancel out. So the only thing that matters is the adjacent side component. So we end up back where we dealt with the one with the ring, which is this is kq over d squared times the cosine of theta is all that's going to matter, because those are going to add up. Now I recognize, okay, fine, d squared is a constant, k is a constant, q's going to be a constant, except q is kind of in a weird spot. So I'm going to want to slide along the outside as I go from one place to the other place. So I'm going to need to think about how q is going to be presented in this problem, because I don't really want to do total q, because q here is different than q here. Okay, so I'm going to think about that in a moment. And then I got my lovely cosine theta. So how much q? So what q is entailed in here? Well, I recognize it's just a lambda, right? It's a lambda charge per unit length. Then I recognize, okay, so I need to multiply by the length. Well, the length of this arc is going, the length of this arc is, we use what's called the arc length, right? And that's equal to that. And that would be equal to the little bitty bit of q that I have locked in my spot, which we usually write as dq as we get more finessey at this calculus stuff, okay? Now, what's interesting about the arc length is we had a formula last year that we learned in trigonometry pre-calculus, which said the following. It said arc length is equal to r theta. And that's equal to my little bitty bit of q that's trapped in this little bitty spot up here. Okay, so I'm going to replace q with k over d squared, which is going to be r squared because that's our radius. And I've got a lambda, and I've got an r, and I've got a theta cosine theta, except that I just multiplied a theta times a cosine theta. So I recognize, aha, I'm going to have to write that theta as a d theta because I'm multiplying. So you got k lambda r over r squared, and that theta becomes my d theta, and I go cosine theta d theta, and I'm going to start at negative theta, negative theta 1, right? This theta 1 would be the bottom angle, to theta 2, which is my top angle. Great. Now I recognize some things. I can get rid of these. I can pull out a bunch of garbage. Equal my electric field. So my electric field is going to be equal to pull out my k, my lambda, my r, none of those matter. And I've got an integral from theta 1 to theta 2 of cosine theta d theta. There's a couple things that people want to do from time to time. I should go ahead and make this a negative theta because I made it symmetric to theta. There's a couple things people recognize. You can make the argument. You can make the argument that these are symmetrics, right? So I'm just going to do half and double it. Or you can recognize that when I put a sign in here, I'm going to take the derivative to be negative sign, and that's going to take care of it because the bottom quadrant and the top quadrant sign is negative down here and positive up here, so it's going to take care of it anyways. Did I pick up a negative along the way? I did not pick up a negative. That's interesting. I didn't pick up a negative. Well, never mind. Not to worry. So this becomes negative k lambda over r, and then this being not negative, sorry, I'm making it negative 82. So negative sine theta. And that's going to be from theta, negative theta 1 to theta 1. Okay, where my theta was for the angle. And then if I go to do the problem, I'm just going to plug it in, and I would get negative k lambda over r sine theta minus a negative k lambda over r sine negative theta. Fair enough? All right, and then that's how you're going to get that done. Okay, so what's the key step here? Key step here is recognizing that Q can be written as lambda, your charge per unit length, times your arc length, which is r theta. Recognizing that theta right here is going to become a d theta when we go to multiply, because we got a theta already in the problem. We can't multiply two thetas together if they're changing, so therefore I have to change one with respect to the other. And then I also recognize that only thing that matters is the left-right components, the adjacent side, because the up-down is not going to matter at all. Okay, and then that's how I get to that expression. Okay, so not much else for you to do today. Review these, look at them, make a couple notes for yourself. Again, you might want to note this, and you might want to note the cosine theta part of this problem, because again, what's going to happen is typically the way AP Central writes these problems is they're going to give you the semicircle, then they're going to say the proper expression for the electric field is this. They're going to give you the answer, and you're like, okay, well, and then they're going to ask you, how do you get to this answer? So you're going to have to work your way through the problem to get to the answer. Okay, so really, they expect to see this kq over d squared on all these problems. They really expect you to do that, to write kq over d squared. Then they expect you to use these two ideas. If you're going to do a semicircle, to use different ideas for the disk and just different ideas for the ring and for the line of charge. I also point out that the disk would be really hard to do without the ring formula. So very seldom you see the disk problem. The disk problem would be hideous in the extreme. Okay. But that doesn't mean you don't have to do it, because they specifically list one of what you should be able to do. Okay. All right. So you have this, and then you can do your homework. Again, you don't have to drive this from scratch if you don't want to, but practice is not the worst thing you could do. See you on Wednesday.